Okay, welcome back. We'll continue with our study of constitutive relations. In the last segment, or the last two segments perhaps, we took a small detour. And in particular, we took that time to consider a boundary value problem, an initial and boundary value problem, in the context of fluid mechanics. Okay, so we saw how we apply the equations, how we use various assumptions and this so-called semi-inverse method to see how things work out in one particular and fairly familiar case for fluids. Okay. Today we will return to the main line of our study, which is constitutive relations, and we're going to talk about a very important aspect of it, and we're going to do this in the context of solids. Okay. We are going to consider the question of material symmetry, okay, or isotropy, more generally put. Okay, so we are going to study, starting with this segment, perhaps one or two more segments on material symmetry. Okay. More specifically, we are going to consider the question of mechanical isotropy. Okay. Let me start by saying what we mean by isotropy. Chances are this is a term that's familiar to you. Okay, so just think about where you've previously seen the use of that term. Okay, chances are you've heard of a material being referred to as isotropic or anisotropic. The term isotropy, it's a mathematical term. It simply means invariance with respect to direction. Okay. As a very special example of this, this tensor that we've been using often, right? I've often referred to this as the second order isotropic tensor, right? Okay, and the reason we say this is because we know that the action of, we know that this belongs to S3 plus, right? And the reason we call it an isotropic tensor is because we know that the action of this tensor on any object, on any vector, okay, is to return the same vector to us, right? And this holds for any vector. Okay, so what this is saying is that to this particular operator, that vector, right, when operated upon, just stays the same, right, with respect to direction, right? It turns out to be the same with respect to magnitude as well, but right here we're focusing on the directional aspect of this property. Okay, so this tensor in particular sees all of space as the same, right? Because it looks at all directions in space, and all directions in space are represented by vectors, right? It sees them all as being the same, right? And essentially returns the same direction back to us. Okay, so that's an example of the use of this term isotropy. What we're going to do, however, in the context of material symmetry is a little different. Okay. Here is what we're going to do. We're going to do this in the context of solids, though it can be applied to fluids as well. It's perhaps a little better known in the context of solids, so we'll study it in that setting. Okay, so we will consider it So we will consider material symmetry. Okay, not just for solids, but for the kinds of solids we are considering here, which is for hyperelastic solids. Right? And you remember that the term hyperelastic solid really is a statement on how we are modeling the solid. Okay, so we know that this solid, if we call it hyperelastic, we know that we have for it a strain energy function density, strain energy density function, right? Okay, all right. So we have this object, right? So what we're saying is that there exists a function psi, okay, which is a mapping in general from a space that takes tensors, right, and returns to us a real number, which is the strain energy density function. Okay, and of course what we already know, and we spent quite some time studying this, we know that the requirement of material frame invariance or objectivity right. So material frame invariance implies for us that psi, which first of all from the notion of hyperelasticity, actually we can probably write it right here, right? Okay, F being the deformation gradient tensor. Okay, we know that material frame invariance says that this function psi of F can be a function of F only through its stretch tensor, through the right stretch tensor. And in fact, once we make that observation, we immediately have these other representations for it, right? In terms of the right Cauchy-Green tensor, or in terms of the Lagrange strain tensor. Okay, so this is where we are starting. So let's draw a picture for what we will need here. All right, we have our basis. Let me label this basis E1, E2, E3. Now, let me draw the reference configuration of the body. Okay, omega naught, right? And that is the position of a point X. Okay. Now, we are going to apply some deformation on this body, all right? And as always, that deformation is, that motion is denoted by phi. It takes the body to some deformed configuration. Okay? Right. Now, remember that when we made our arguments about material frame invariance, we were asking ourselves the question of what the strain energy function should do under superposed rigid motions on this current configuration omega t, right? This configuration here to the right. Okay? Now we're going to use an operation that is related but is different both mathematically and physically. We're going to ask ourselves the following question, right? We're going to look at this point here, and let's suppose that the point X it represents a neighborhood. Okay? We are going to ask ourselves the following question. We're going to say that supposing we could represent some microstructure in that neighborhood. Okay? And I'm going to represent the microstructure by drawing these lines. You can think of them as whatever you like. You can think of them as fibers running through the material. You may think of them as crystal planes that you may see under sufficient magnification, right, around that material point. or you may just look at it as lines sort of drawn on the material. Okay? All right. Now we say we want to do something to the reference configuration. Okay? And this is important. This is an important difference from what we did earlier when we were making our arguments about material, frame, and variance, when we did things with the current configuration. All right? In particular, what we want to do is the following. We want to say that, you know, these axes that I've drawn outside, the bases that I've drawn outside, let me suppose that I actually scribe the same basis or the same coordinate system on the material here. Okay? So this 2 is E1, E2, E3. Right? I've just drawn them on the material. Okay? And now I'm going to give that reference configuration a rigid motion. The reference configuration gets a rigid motion now. Okay? All right. So I want to first do this. Okay, now I've got to do a decent job of representing this rotated reference configuration. Okay, reasonable. What's more important is that I draw this neighborhood. Okay, I'm going to denote this neighborhood as X star. Okay, and what has happened in my applying a rigid motion on this reference configuration is that those, that microstructure I drew in the neighborhood around X has suffered a rotation. Okay, and a translation, of course, but a rotation for the microstructure is more important here. So this is what that microstructure looks like now. Right? You may think of them as, like I said, fibers or crystal planes or whatever, right? And in the process, the basis that was scribed on the material has been rotated. Okay, and let's denote these new basis vectors: E1 star, E2 star, E3 star. All right, let's describe this new position, right? We know how to write rigid motions very well now, right? So what we're doing here is, like I've been saying, we have imposed rigid motions on omega naught. Okay, so we should probably call this reference configuration. We've now come to a new reference configuration, if you would like. Right? We've just swapped out reference configurations. And it's okay to do this because you will recall way back when we first introduced the notion of a reference configuration, as we said that, well, this is really arbitrary. Right? So we're allowed to do this. Okay, so we've imposed a rigid motion on omega naught, which now allows us to write these new positions of material particles as X star equals, again, some translation vector, right, plus the effect of a rotation. Okay, and as always for rigid motions, we have C of t is a vector and Q of t, it is a member of SO3, but a member of SO3 that preserves orientations. Right? Well, it doesn't preserve orientations with the rotation, but it preserves handedness, sorry, preserves handedness. Okay, we have this, okay? Now, the question we want to ask is the following. Suppose, relative to the original basis, right, suppose relative to the original basis, we apply a deformation upon the material, right? Okay, and let us suppose also that let us suppose that the way to think about this original basis is when we have the room around us. You have the room around you. I have a room around me. There are walls in the room, right? And let me suppose that this set of basis vectors represents the walls of the room, right? Maybe these are where the walls meet, right? This is how we think about it. This is our original reference configuration. This is omega naught. We are talking of applying a deformation on this material. Now, we want to think of the deformation we are applying as being fixed relative to the walls of the room, okay? And the simplest way to think about this is that, all right, we have this basis. I'm going to have to put it down because I have only two hands here. Okay, but relative to that basis, I'm going to stretch this material. Okay, so I'm stretching it. But if you ask yourself, how are you stretching it? You should think of the fact that you're stretching it relative to the walls of the room. So pick some direction in the room, maybe along one of the corners of where the walls meet, and suppose that you're stretching out a material along that corner, right? And along the line defined by that corner. Okay, this is what we want to think about. Okay, and all right, so that's the kind of motion you're going to apply. All right, so I've taken away my body, but still I'm talking of applying that kind of a motion, right? That is the deformation I want to apply to the body, right? Relative to the walls of the room, relative to my basis, right? So this is the deformation, right? Along this axis. Okay, but then we have applied a rigid motion on the reference configuration, right? So now what you need to think about is the idea that, well, instead of having the body be presented in this orientation to the deformation, this is the deformation, I present the body this way, so you're going to deform it like this, right? Stretching it along the long axis. We're applying a rigid motion on the reference configuration. So maybe we do this, okay? The deformation, however, remains fixed relative to the walls of the room, relative to this basis. So now what are we doing? We've got this body, we're still talking of stretching it along this direction. Understand? So the deformation remains fixed relative to this to the original basis, which is the basis I've drawn here. Okay? All right? I also made a copy of that basis and put it on the original reference configuration omega naught, and you can see it here. Okay? And then I applied a rigid motion to that reference configuration. Of course, it's only the rotational part of that rigid motion that's really important here. Okay? Observe that in doing that, since I've applied this particular motion upon the configuration, we know that now our newly placed vectors are E1 star equals Q E1, and more generally EI star equals Q EI. Okay, we know about this. All right. The question we want to ask now is the following. In this material, or on this body which has been rotated, of course, now if this body contained microstructure like I've drawn on the slide, in rotating the reference configuration, that microstructure has also been rotated, right? And that's what I've drawn in the new configuration omega naught star, right? That microstructure has been rotated. However, I'm going to deform the material and therefore the microstructure along some directions where those directions are defined relative to the walls of the room. I'm still going to put it this way, okay? However, the material is now presented to this deformation with a different orientation, right? Okay, so as you can imagine, if I'm going to take these two pictures here and stretch them along the E2 axis, right? The fact that the microstructure is presented differently to the original E2 axis could have an effect. Okay? This is what we want to address. What is the effect of rotations on the reference configuration when the material has some microstructure? Okay? All right. So essentially what we want, so let me put that down. What is the effect on material response, on material constitutive response, shall we say. Okay. More precisely, what happens with psi? Okay, and let me write psi in the simplest form, in the original form that we use for hyperelasticity, which is psi as a function of f. Of course, we know that material frame invariance has to apply. Okay, but still, let's just work with this version. Okay, right. And note that this is an important question because, of course, if the material had no microstructure, right, if there was really, this material were completely uniform, even under a magnifying glass, you could not find any sort of preferred directions or special directions in the material, nothing like that, right? You would expect then, okay, if you were to take a little neighborhood cut out of this material, right, and stretch it, right, I've cut out some little microstructure neighborhood from this material, I'm holding it now, I'm stretching it, right? It matters not whether I present that microstructure, whether I pull out that little neighborhood before I rotated the material or after I rotated the material, right? If I'm going to deform it in this direction, that little neighborhood is going to have the same response, right? But then we want to be able to pose this question. Okay, how do we really pose this? Okay, so the way we pose it is to recognize that when we write the strain energy function as a function of the deformation gradient, you should ask yourself, okay, it's a function of the deformation gradient, but should the deformation gradient that is included in the strain energy function be a deformation gradient relative to surrounding space, or should it be the deformation gradient measured relative to sort of the fibers of the material itself? Okay, so let me write this question. It's going to be written in a fairly colloquial manner, so it's not going to be a very precisely stated question, but not at least the way I write it. Okay, so I'm going to say f relative to ambient space or relative to material fibers. Okay, so the question is, if you are going to write out a strain energy density function for a material, okay, should you be more what gives us a more physical representation of the material response? Is it that we just define the deformation relative to the walls of the room, that's relative to this basis? Or is it that we ask ourselves, well, really the question to address is, how are the fibers of the material being stretched by this deformation we're applying, stretched or compressed or whatever, right, distorted? Okay, so that's what I'm trying to ask you here. Okay, all right. And this matters, okay, and the reason it matters is that the two deformation gradients are going to be different. Okay, so for this picture, we already have f equals partial of phi with respect to capital X. Okay, right? But then we need to ask ourselves, well, is that what matters, right? Okay, so we have f relative to the walls of the room, which is partial of phi with respect to x, right? And this is the sort of deformation that we're holding fixed. Okay, so is it that this matters? Okay, I don't need the question mark there. Okay, does this matter, or does f star which is relative to the material fibers. And remember, x star now gives us the material fibers because that is how the material has been rotated. That's the new sort of orientation of the material. Okay? Okay, so that's the question we are trying to ask ourselves. Okay? Clearly, if we want material response, it is this one which matters, right? Okay? Especially if you think about the possibility that the material may have some microstructure, and in rotating the reference configuration, we are now presenting that microstructure differently to the deformation that we are applying relative to the walls of the room. Okay? It can make a difference. Okay, so, right, so F star is the one that matters. Okay? How do we write F star? Right? Or correct? So note that F star from the chain rule is partial of phi with respect to x, partial of x with respect to x star. Okay? But for the rigid motions on the reference configuration, right, where c and q are functions of time only, we know that x equals x minus c acted upon by q inverse, but q belongs to SO3, so that's q transpose. Okay? What this gives us then is that partial of x with respect to x star equals q transpose. Okay? All right. So finally we get F star equals F q transpose. Okay, where of course we realize that this is F. Okay? So the whole point of what we're going to do now is to ask ourselves what happens with psi as a function of F star when compared with psi evaluated with F. Okay? This is the question we are going to address, which we will do in the next segment.